Okay, so it's my great pleasure to welcome and introduce Martha White. So she's an associate professor of computing science at the University of Alberta, and she's also a PI at AMI. So this is the Alberta Machine Intelligence Institute, which is one of the top machine learning centers in the world. She also holds a Canada CFAR AI chair, and she received recently the IEEE's AI's 10 Top to Watch, the Future of AI. So that's an award that she got in 2020. And she also has authored more than 50 papers in top conferences and journals. She's an associate editor with TPAMI, and she often serves as area chair for various conferences in AI and machine learning. So that includes ICML, NeurIPS, AAAI, HCI, and she was also co-program chair for ICLR recently. So in terms of research, she focuses on developing algorithms for agents that continually learn on streams of data. And this is with an emphasis on representation learning and reinforcement learning. So without any further ado, so I'll let Martha go ahead. And the title of her work is Developing Reinforcement Learning Agents that Learn Many Subtasks.
Thanks for that very nice introduction. And it's my pleasure to be here. I very much appreciate the invitation, and I appreciate you taking the time out of your day to come listen to this talk. So I have slides here. I know sometimes people like to follow along on the slides. So I've also posted them on my website, and I put the link here in the chat. All right, so I know this is a relatively diverse group, but I know we're all really passionate about AI. And I really have, this talk is a lot more about a problem setting than it is about answers. And so my goals for this talk are primarily these three goals. I want to motivate first for you that general purpose agents are ones that need to learn many subtasks in parallel. So I'm going to go through a little bit of motivation and examples of the types of problems that I'm thinking about when I say this. Then I'm going to introduce a little bit more of a specific formalism called the continual subtask learning formalism, which is going to help us actually develop such agents. And then along the way, I'm going to point out for you what I think are exciting open research questions, ones where actually you might be able to work on them as well. And I'll also tell you, of course, about some of the progress we have made to some of these research questions. This is a relatively small group, so I really hope that you'll just interrupt and ask any questions, and I'll also be monitoring the chat as well. All right, so let's get started. Again, because I said this is a relatively broad group, I'm going to give just a brief overview of the reinforcement learning problem setting. So, when I'm talking about this setting where we need general purpose agents, it's really also going to live within the regular reinforcement learning setting where we have an agent, it's in some states, maybe it's trying to control parts of this plant, like it needs to set pump speeds and decide on how many chemicals to put in the plant. So it's going to take an action every step. It's going to transition to some new state, and that state might consist of many sensor values, for example, and it's going to receive a reward depending on how good or bad that action was. Now, its goal in the end is to learn a policy called pi. I hope you can see my pointer here, where it's actually maximizing its expected return, and the return is the cumulative reward into the future, discounted possibly by some gamma that might be less than 1. And the discount tells us that the agent should care more about immediate rewards and less about future rewards. All right, so because of this, the agent's goal is to learn this expected return. A central part of many reinforcement learning algorithms is actually to try to approximate this expected return. And those approximations are called value functions. And so there's different value functions that the agent might try to learn so that it can actually solve this problem. I'm just going to tell you about a few of these because we're, of course, going to use value functions later when I tell you about what some of the subtasks are going to be. Okay, so a value function vpi is exactly this term here that I just told you about. It's the expected return under this policy pi. So if I'm in some state, and if I were to execute pi forever onward from here, so execute my policy pi, then I would receive this return GT, and this is telling me my expectation over all the possible trajectories of returns that I could see. So the nice thing about this value function definition is we can actually write it recursively in this way, where we say the value function is the immediate reward plus gamma times the value in the next state. And this recursive form is exactly what a lot of algorithms in RL exploit. They give us this nice Bellman equation, and then we can actually use this R plus our value in the next state as an approximation to our return. And so we're going to use this bootstrapping in our TD algorithms, including the SARSA algorithm I'll show you on the next slide. Okay, in addition to value functions, we're also going to want to learn action value functions, which tell us not just from the state what would be my return. It's if I was in the state and then I took this action and then I were to follow my policy pi, what would be my expected return? Very similar idea. But action values allow us to then also learn a policy because we're going to greedify according to those action values. And then we're going to get a better policy. And we're going to do this repeatedly. And finally, some strategies also directly estimate what's Q star, which is the action values for the optimal policy. And that's methods like Q learning. Okay, so what would an example agent look like? And then I'll tell you what I feel like might be missing from this very standard agent. So a commonly used agent is called SARSA. The SARSA agent is going to learn a policy through trial and error interaction. And just to be very concrete, so you can have a sense of what this looks like, and we're actually going to step through what this agent would do. Okay, so the agent's goal is to learn or approximate these action values I just told you about. Its approximation Q hat. It's going to have some parameters W down here that it's going to be estimating. And then its policy is going to put a max on top of that, or often a soft maximization on it. Let's say with this Boltzmann policy, where it's going to pick actions proportionally to the magnitudes of these action values. So higher action values, it's going to be more likely to select those actions. Lower action values is less likely. Okay, so the interaction is going to proceed as follows. It's going to be in a state. The agent's then going to take an action AT from its current policy. It's going to transition to its next state and also receive a reward. And then it's going to preemptively decide what it's going to do from the state as T+1, because it's also going to use that in its update. Okay, and then it's going to, based on this new experience, it just generated new data for itself, saw something about how the world works. It's going to update its value estimates Q hat. And a particular Q hat is trying to estimate the action values for the current policy. So what this update is what looks like a very standard linear regression update rule, where we have a given target, an estimate of the return, and we're trying to move our current estimate of the action values towards that return, where this is the gradient of our function approximator. So what looks like a very standard linear regression update, and the only thing that makes it not actually a linear regression update is that our return isn't going to be a true unbiased sample of the return from the environment. If we wanted that, we'd have to roll out the policy and wait many steps to see it. Instead, we use this nice recursive form that I mentioned, and we're going to bootstrap off of our own guess of what we believe the return is going to be if I were to continue following policy pi. And here I sampled A according to pi. Okay, so that's generally what the RL setting looks like, what an agent might look like when it's interacting with the world in an MDP. And now we can ask, is that good enough? SARSA and algorithms like it, like Q learning, are still very commonly used algorithms. But we can ask ourselves, how far are we going to get with this very simple update? And I'm going to argue that we're going to need to have more. In particular, we need to have the agent learn about these modular components called subtasks. So why is that? In particular, we're going to need more for the types of problems that I think are a little bit more interesting than the simpler problems we use SARSA for. In particular, we're going to need it for this setting called the lifelong learning setting. Okay, and in this setting, it's really characterized by two key properties. One is that the agent's going to interact in the world for a very long time. So there's going to be many steps of interaction, a lifetime of interaction. And the environments themselves are going to be potentially vast environments, more complex environments. So some examples of what I would call lifelong learning settings might be having an assistant agent that's interacting with people. You might have a robot that's actually navigating a city. The city is vast and complex. Maybe you have an agent that's controlling energy usage for a network of buildings, and there's always new buildings being added to this network, and it needs to contend with this growing problem. So to me, the reason I want to focus on this lifelong learning setting, again, characterized by these two properties, is that it's, to me, actually the real setting. It's a very practical paradigm. So real world environments really are complex and potentially vast, and they really do require the agent to run for a long time. Sometimes I think lifelong learning is associated strictly with AGI, and it's kind of seen as this is separate from applications or the practical setting. But I really believe that we need to tackle this setting if we want to build agents, tomorrow for these complex environments that we care about. All right, so let's anyway think about an example of why an agent might need something a little more than SARSA, and I'll just use these names that I've given these. Let's call this courier bot that's trying to navigate a city. Okay, so if we were to imagine an agent that actually has to do this task, we have this RL agent. A natural thing that it should have is the ability to make many predictions about the world. So it's likely going to be helpful for this agent if it can answer predictive questions like the following ones. What will happen if I pick up this object? Or how many steps until I get to the door? Or how much longer can I drive before I need to recharge? Or, in a stop bubble here, if I navigate to the lab, would try to plug in succeed? If it can make all these different types of predictions about the world, then it actually has quite a lot of knowledge about how the world works, and it should be able to leverage all those predictions, which I'll call subtasks, in order to do a better job of its main task, which is actually currying items across the city. Okay, and so why this is all part of the lifelong learning setting is that under this long sequence of interaction, it's sensible that the agent would spend some amount of time actually accumulating knowledge about its environment. If it knows it's going to interact in this world for a long time, constantly trying to maximize reward, it's worth taking the time to learn about that world, so learn some knowledge about the world, so that when it sees new situations, it can actually learn and adapt faster in those new situations. And it's going to see new situations because the world's vast and complex, and because it's going to be interacting for such a long period of time. And in addition, in these large worlds, the world can also often look non-stationary, even if it isn't non-stationary, because the world is vast and the agent is limited. So the main idea here is that accumulating this knowledge is going to be worthwhile in these lifelong learning settings. And the way we're going to take this more abstract term of knowledge is we're going to encode our knowledge as subtasks. So what we would like the agent to do is learn these modular components that can be reused. We'll call those subtasks. And I'm going to particularly focus on two types of subtasks. And those are control subtasks and prediction subtasks. And we're going to encode those as the control subtask as options or skills. And for the prediction subtasks, we're going to encode them as general value functions. So let me just tell you what those are through this exact same example. Okay, so here's two things that the agent might actually want to learn about, two subtasks that it might want to have. Okay, so one thing that could be useful for the agent to know is to learn a policy pi that navigates to the lab. It maybe needs to get to the lab in order to recharge. So this is a policy it's going to be constantly reusing. Learning it once and then reusing it is going to be beneficial. Something like this policy is often called an option, or sometimes it's also called a skill. Okay, so that's called a control subtask because it's learned a policy to accomplish something, some subcomponent of that larger world. And then a prediction subtask could be something like, what is the probability I will successfully plug in if I run the navigate to lab option policy pi? Okay, so here this is not specifically a control question. It's actually just asking, what's the outcome going to be if I were to run some policy? So it's a policy contingent question. And it's, again, a useful prediction to have, because if the answer to this question is that the probability is low, then you're not going to go run that policy. Instead, you're going to do something else in order to find a way to recharge. Okay, so the first one is maybe more obvious how it is that we could learn subtasks. We would use regular RL algorithms. Maybe we could even use that SARSA algorithm for learning that policy. But general value functions here, I haven't told you what these are, and I haven't told you at all how you could learn a question like this. So let me tell you how we're going to use these general value functions to learn this prediction subtask, or this very briefly, because I have more things I want to tell you about.
Sorry,
yes.
A question: is the environment assumed to be stationary during this lifelong experience?
Great question. I mentioned the word non-stationary there. I like to imagine, this is a bit of a philosophical debate that I'm sure other people here have had as well, but I like to imagine that the world underneath is actually stationary. Underneath everything lies a Markov decision process, but things might look non-stationary to the agent either because of partial observability or because of its own inability to represent things, like its own features or function approximator has made things look partially observable. So I'd like to imagine that the true underlying world is stationary. Does that answer your question?
Yes, thanks.
You're welcome. There might be an additional purpose to that question. So if there's a follow-up, do feel free to ask. Okay, but partially observable, definitely. I mean, in vast complex environments, it would be very unlikely to have the true state that's given to the agent. It's going to be partially observable. Okay, so what is a general value function? Discussing general value functions could fill an entire talk. So I'm just going to give you a little bit of an idea of what this is. Okay, so just reminding what our goal is to represent this predictive question. And what's the probability I will successfully plug in? Okay, so there's this recent introduction called general value functions, introduced in 2011, that recognizes this really cool property. It says that value functions let us learn about cumulative rewards into the future. And so really it's a prediction about what the return I'm going to see under a policy. Now, I don't just have to ask predictive questions about the reward. I can replace the reward with any signal of interest. Let's call that a cumulant. So I can accumulate any signal into the future. And now the value function, or the expected value of that cumulant, is going to tell me something about the future, not necessarily something I want to maximize, not necessarily the reward, but it'll just be able to answer this predictive question. So let's see how you would write down this question. So we're trying to figure out what the probability of successful plugin is. So we can define this new cumulant. You can mentally map this to where the reward would usually go. That says I'm going to receive a 1 if I've plugged in and a 0 otherwise. Okay, now we can think about what the meaning of this return is going to be. So we're saying if I were to follow my policy pi, which is the navigate to lab policy, then the cumulant I'm going to see is I'm going to see 0 plus 0 plus 0 all the way up until at the very end, and then I'm going to terminate. I'm going to see a 1 if I successfully plugged in, or if I'm never able to successfully plug in, then I'm always just going to see zeros. So we can imagine what these returns might look like. If I'm never able to plug in, then I'm just always going to have 0. My expected return is going to be 0, so my probability is 0. If deterministically I'm always able to eventually get to plug in, then every trajectory here is going to have 0, 0, 0 plus 1 at the end. So my expected return is going to be 1. So my probability of plugging in is 1. And then more likely it's going to be something in the middle. Some trajectories will be successful. Maybe I had enough battery and cats didn't get in my way. And so I managed to succeed 70% of the time, and 30% of the time something goes wrong and I'm unable to succeed. So then my Q pi of SA would tell me 0.7, 70% probability that you will successfully plug in. So these are the ways that we're going to use general value functions to specify our prediction subtasks. And then actually, we're not going to need too much more to know about exactly how it is we're going to learn these options in general value functions. But the reason we restrict ourselves to these two types of subtasks is we get to use all the same machinery that we're used to in RL to learn all of these. We're still going to use the same value function learning algorithms, and we can use, again, even similar algorithms for learning the options as well. So it's an elegant way to encode both prediction and control subtasks. Okay, before
Excuse me, Martha, can I ask a question? Sorry.
Yes.
Yeah. So in this slide, so when you've defined the cumulant, can you say how is it different from a reward? Like I don't think you have actually defined the reward function in this case yet, right?
Great question. So whenever we're talking about a predictive question, in some sense we've discarded what the real environmental reward is. I don't care about the environmental reward for this question because my goal is just to answer what's the probability I'll successfully plug in. This happens to look something like a regular reward because it looks like a +1, for success and a 0 otherwise, which is maybe an unfortunate thing. So let me give you an example of another cumulant we could have used. Maybe instead of what's the probability I will successfully plug in, I might want to know what's the number of steps I will take until I successfully plug in which case my cumulant could be 1 on every single step. And then this accumulation would count the number of steps it takes me on average to get to the successful plugin. And that's definitely not something you would want to maximize. You wouldn't want to maximize the number of steps to get to plugin. And you're specifying your cumulant so that you can make the prediction that you're intending to make, which is what's my expected number of steps to plug in. Does that make sense?
Yeah. Thank you.
So that's why we like to use the word cumulant, because we're absolutely not trying to maximize it. We're only trying to predict it.
Okay, thank you.
Okay, so I sort of made this pitch about why that we want to move to this setting where we're going to incorporate these subtasks. I think it's useful just to ask a little bit, what are people doing right now? Are they using this, or if they're not, why aren't they already learning all these subtasks? And what has been done historically? So you can ask, what's the alternative to learning subtasks? And today, most RL systems don't really focus on doing this. Of course, there is some people who are equally interested in learning options and general value functions, but many RL systems typically just use end-to-end learning of policies, say with a SARSA algorithm or Q-learning, and where they have no models, they have no options, they have no general value functions. And I would argue that that's actually just very sensible for many of the environments we currently tackle. So for smaller environments, we can actually cover those environments reasonably well that are stationary, or at least they look stationary to the agent, they're especially fully observable. There's really not much need to learn secondary objects. You spend this time accumulating the knowledge when you could have just gone ahead and directly learned the policy with SARSA. So it's really sensible in these environments, in those environments, to just use this end-to-end approach. And it helps explain why this has not been as big of a question and why many methods do just use end-to-end learning. But now when it comes to more complex environments, the types of ones we would like to start developing agents for, it's actually not too controversial that we're going to need some of these secondary components, let's say subtasks. And really, actually, it's of course a very old idea in AI. So by no means are we proposing that learning multiple tasks or subtasks is new. This idea has been around for a very long time, and it's even been around for a very long time in lifelong learning itself, where, you know, or much earlier work by Thrun looked exactly at how do we learn subtasks. Now, the main difference about what I'm pitching here and maybe what's done in these older ideas is a lot of the older stuff looked at how we're going to learn these subtasks sequentially. And what we really want to be able to have is the agent learn many subtasks in parallel, because that's going to be much more efficient. The agent can learn many, many more things, and it really does just have one single stream of experience. So it's difficult to try to learn many of these tasks if you have to sequentially order them. Now, it made sense again to do that earlier because it was conceptually simpler. It had been the first time you're tackling the subtask setting. So there, the experimenter also designed the sequence of tasks for the agent. And now if we're learning many tasks in parallel, it also doesn't make a lot of sense for us to specify that. That would be very difficult. And it makes a lot of sense to now start pushing that into the agent and telling the agent to decide what subtask it's going to focus on learning and where it needs to go in the environment to actually better learn those subtasks. Okay, so this more modern perspective where we're thinking about doing all of these things in parallel raises some really interesting questions. One of those is, again, when things were sequential, it was very naturally on policy. So I was just focused on one task. It was exactly about the policy I'm currently following. And we had nice algorithms for on policy learning. But once you move to the parallel setting, now things become naturally off policy, which means the agent has to reason counterfactually. So if I'm currently doing some behavior, but I really want to also learn about the navigate to lab policy, then that's exactly off policy learning. I need to counterfactually reason about what would have happened if I were executing the navigate to lab policy, even though I'm currently following a different policy. And that's actually a bit more difficult. And the off policy algorithms in RL for a long time were known to have divergence issues and were somewhat unstable actually in the off policy setting. So what's somewhat exciting now in the more recently is that we actually finally have tools to really properly explore this problem setting. So the goals of this problem setting have been around for a very long time in RL and in AI as well. But you know, only recently did we actually get very significant improvements in off-policy algorithms. And so I see this now as the golden time to take this very big and old question and revisit it with our fresh new tools and really make significant progress towards it. All right, so what I'm now saying is that you know, our goal is to tackle this setting, and we're really going to wholeheartedly commit to what I'm going to call this inductive bias. So our assumption is that it is effective for the agent to learn these reusable modular components, which I'm going to call subtasks. So under that assumption that this is something that our agent should do, I've now hopefully motivated that sufficiently for you, and you're very excited about this problem setting. Now, under this assumption, there's two really main things that the agent needs to ask itself. So one is, how's the agent going to discover which subtasks are useful? And then once it's discovered those, you know, it has its collection of subtasks, how is it going to learn them as efficiently as possible? So presumably it wants to use those subtasks to maximize its reward in the environment. You know, all these predictions, they should be accurate so the agent can use them effectively. So it needs to figure out how to learn those efficiently. The first question, the discovery question, is a very interesting and hard problem. And as usual, we have to start with one of these problems. So we're starting with this question, which is, how can the agent learn these subtasks efficiently?
Sorry, Martha, can I ask a question? So I'm still unclear. With the definition of the subtask. So is that also like a sequence of states, or you know, what exactly is a subtask? Do you have a definition like you mentioned somewhere that I missed? I'm sorry if that is the case.
You know what, you're right, I haven't been that precise about it. And I'm not actually going to get any more precise about it, except for we will see a few examples of what they are in little toy experiments that we have. So let me just tell you more specifically what it would be. A subtask, you know, the word subtask just means we have our primary task, which is maximize reward. We do just still have an RL agent. And a subtask is any control, like an option or any general value function, which gives you a prediction that the agent is going to use towards that goal. So a subtask would be, for example, one of these general value function predictions. That is actually, its subtask is to go learn the value function, to go estimate this QPi that gives it an accurate prediction for this question. So that's one type of subtask, a prediction subtask. And the control subtask is go learn the policy that navigates to the lab. So it would have to learn either, you know, a QPi or Q star for that policy pi. Does that make sense?
Okay, so the general value function is the subtask. So you have given two types of subtasks, the control subtask and the prediction subtask. So this means that subtask is something other than the prediction or the control problem here. So with using this robot example that you have on this slide, can you say what is the task and what is the subtask in this example?
Yes, good. And in fact, maybe this is a good chance to clarify too to what is usually described as tasks. So it's not uncommon, let's say in an RL setting, to say that I have multiple MVPs, or I have, you know, task 1, I learn how to play tennis. Then I have task 2, I learn how to play badminton. Then I have task 3, I learn how to play rugby. Okay, so I don't mean tasks in that sense. The task, the primary task, is there's always just one MVP. It is the world that the agent is living in. So for this courier bot, it's living in a city, and its primary goal is to maximize reward from the environment, just like the regular RL setting.
Okay.
So it has that environmental reward. Let's imagine its reward is every time it successfully drops off a package, it gets plus 100, because that's how much money it makes. And that's the only reward it receives in the environment. Maybe it gets a little negative penalty for each step it takes because it uses up some gas or something, or electricity. And then as its subtasks are all these secondary objects that it learns to help it actually solve its primary task, which is to maximize reward. So it'll be useful to have this option, because it can use that option either to directly execute the option, to get back to the lab to charge up, or it could do planning with that option. So it's going to use that, it could use that option in different ways. Or
yeah, that makes it clear. Okay, yeah, thanks a lot.
Yeah, so yeah, task in this sense doesn't mean like ability to play tennis and the badminton and so on. It's whatever things the agent's discovered for itself, predictions that it should learn or options that it should learn that are then going to help it maximizing reward. Thank you so much for clarifying that. Right, okay, so this is what the focus of the rest of the talk is going to be about. How can the agent learn these subtasks efficiently? Great. Okay, so this is what I'm imagining our agent looks like, our lifelong learning RL agent. It still has the same environment interaction, so the agent's in this gray box. It's just now internally, we're going to imagine that we have this additional component that we have built in. That's why I'm calling it an inductive bias. So now the RL agent here still wants to adapt its behavior so that it maximizes this reward signal from the environment, but it also wants to ensure that it gathers data, so it directs its actions, so that it's also learning about all these tasks, subtasks that it cares about. So it has these N subtasks, and it would like to learn those efficiently as well. So the way that we're going to do that is we're going to imagine that we're going to take some information from these subtasks that say, after I received this experience from the world, I was able to update my my task weights. And then I'm going to have some intrinsic reward that is generated that reflects something about how much information was gained from that data. We're going to talk more about how we specify these intrinsic rewards. But assuming that we have this module that figures out what the intrinsic reward is, now the agent's goal is to maximize both this external reward and this intrinsic reward. So it's going to, let's, for example, add them together. This is the problem setting I would like to work in, but still there's going to be now a lot of complications in this setting. So now we have to think about what are the learners what algorithms are we going to use for these subtask learners? How are we going to define this intrinsic reward? And how is the behavior going to balance between the environmental reward and this intrinsic reward? So there's a lot of moving components to that system. And it's always good to step back to the simplest setting first and try to understand things there. So what we're going to do is just first focus on understanding how are we going to develop algorithms that maximize this intrinsic reward? In other words, we're going to just care about how can we get an agent to gather data so that it learns subtasks as efficiently as possible. This is a lot like the active learning setting. We're just asking, how do we go get data that makes us learn prediction problems, for example, more efficiently? So that brings us finally to our continual subtask learning problem setting, where the diagram looks very similar to before, but now we're going to imagine that we have no reward here from the environment. That's not our main purpose here. So we have no reward from the environment, and the behavior's primary job is just to figure out how to act so that it's going to maximize just this intrinsic reward. And so maximizing the intrinsic reward is going to help us learn all these subtasks. And so this intrinsic reward is going to be defined this way, where we assume for task 1, we're going to be able to compute some intrinsic reward that says how useful was the data for task 1, how useful was it for task 2, all the way to task n, and we're just going to sum those up and tell the agent to maximize that sum. Okay, so one way we can start thinking about this problem setting is we now have at least simplified this a little bit, but now we have 2 main interacting components. We're going to have what should we use as our learners for these subtasks, and the other technical question we're going to have is what should the intrinsic reward be? So let's start off by thinking about what would be the best thing, an idealized system if we could have it. And for me, this would be my idealized system. So what we really want is sample efficient subtask learners. So a natural choice there, if we could have it, would be to have Bayesian subtask learners. So each subtask is going to have associated parameters W. They're going to maintain this posterior over their weights given the data they have seen so far. So by time step T, they'll have seen this sequence of interaction in the environment, S0, A0, S1, and so on, where the actions are going to be selected according to the behavior. And this posterior is slowly going to be shrinking around the weights as the subtask gets more and more data. Okay, so this subtask learner is particularly great, like I said, because Bayesian learners are going to be very sample efficient, assuming we've picked good distributions and the priors are all good. But the other thing that's very nice about using a Bayesian subtask learner is that the intrinsic reward is going to be easy to specify. And in particular, we can get it to exactly equal what's called information gain or mutual information. Okay, so the idea here is that the intrinsic reward for the jth subtask is going to be defined as the KL between my posterior of my weights before I saw my new data and the posterior after I incorporate the new data that was just generated. So my behavior policy just took an action. It caused us to see a particular experience tuple, ST, AT, ST plus 1. And now that new information about how the world works is given to each of the subtask learners. And however much this posterior actually changed, however much it concentrated and the entropy was reduced, is going to cause a higher KL term here. So if that experience was very helpful for identifying what these weights should be, the posterior is going to concentrate more, and we're going to have a high KL. If, on the other hand, the experience was not useful at all, it doesn't tell the agent anything new, then maybe we're going to see very little change. And so then it wasn't a very useful sample. There wasn't a lot of information gained for that subtask learner. So hopefully this helps make a little bit more concrete what this setting looks like. And one thing that it can be useful to do is, in addition to an idealized system, it's good to contrast to what would be a bad system. And then what we're going to do is just go through a little experiment that we did in the bandit setting, where we're going to see how important it is that we specify both the subtask learners and the intrinsic reward carefully, or these components can interact in surprising ways that cause pretty bad performance of the whole system. So let's think about now.
Question.
Yes.
So just to clarify, the thing you're trying to predict is whether the task was, whether the actions, the behavior that you did was useful for that task?
That's right. Yeah, our intrinsic reward hopefully reflects, so the agent is trying to maximize its intrinsic reward. So it wants to know, was the action that I just took good or bad? So if the action is good, if it generated data that was useful for the subtask, and that data would be useful if it had the most information gained for that subtask.
Right. Okay. So then does that help defines the reward, or the reward is defined separately from that, saying these are examples of one subtasks, actions that were good for subtasks, and you're trying to predict them?
Right. It's defined internally to the agent, so we get to define the intrinsic reward, and so we have.
Okay, that's defined already.
That's right. So we're defining intrinsic reward to be exactly this because it should reflect, it reflects exactly what we want it to reflect. It gives a high reward for actions that cause lots of learning, and it gives low reward for actions that were not useful. So if the agent was in some start state and it just chose to take the same action over and over again and stay in that state, that would be much less, it would produce much less reward, intrinsic reward, than going and exploring new states that I had never seen before.
Right, because it's learned already. Yeah.
Right. So we want a reward that encourages the behavior to do the right thing, which is to go get data that's helpful for the subtask learners. That is its primary goal.
Great. Cool. Thanks.
Thanks for the question.
Yeah, can I also ask a question?
Yes.
Yeah, so could you explain this, what information on this page using the previous example? For example, suppose the subtask is how many steps you're going to take for the robot. What is the posterior here for that task?
Yes, that's a great question. Okay, so for example, the parameters for such a thing would be the parameters to the value function. So let's say we're trying to estimate this expected return under some policy. And let's say those parameters are for a neural network. And so that's a value function is a neural network learner. And now maybe you could use Bayesian neural networks, for example, to approximate this posterior. I'm going to be honest that Bayesian methods are not that common. So like learning Bayesian, maintaining posteriors for value functions is not that common. If we were to say something like, so if we were to do something simpler than just a value function, let's imagine you were just trying to predict what is the value of sensor 1 that you're going to see on the next step, because you feel like that would be helpful. That would be a standard regression problem. You can imagine the weights are the weights for a linear regression subtask, and then the posterior would be obtained through Bayesian linear regression.
Mm-hmm.
Does that make sense?
Could you take, so I still don't understand in the case where like, if the subtask is like predict how many steps, I just cannot wrap my head around that. So you basically give me another example. What if it's the original example, or like what if the subtask is what's the probability that I'm gonna succeed in this current policy?
Sure. Okay. I'll go back to that example, even though it's not that common to use Bayesian things in RL.
Oh, okay.
Okay. So the weights would be the weights for the action values. So let's imagine the action values also have some linear features. So let's say you have features XSA, I'm just going to type it this way in the chat, that are the features for a state in action. We're going to approximate our Q using features. And we're going to learn some weights. So we're going to learn this linear function of features to estimate our Q. And that Q is exactly that expected return that I mentioned, this cumulant into the future. Mm-hmm. So what you would do for the posterior is you might, again, do something like Bayesian linear regression, where we're learning a linear regression solution for our action values that's trying to estimate this return, where the return is going to be samples like 0, 0.7, 1, and so on. Mm-hmm. Okay, and then the posterior for these weights would be the ones given to you by Bayesian linear regression, which would be that you would have this. So I don't know if you know how the Bayesian linear regression update looks like, but you're going to have these. You're going to start off with some mean and variance over your parameters, over the parameters W. So you're going to have this vector. So you're going to have a vector mean as well and a vector covariance. And then your posterior is going to update that vector mean and vector covariance for the actual parameters.
Mm-hmm. Okay, I see. Thank you.
You're welcome. Now, this hypothetical idealized system isn't actually going to be the one that we're really going to use. I mainly wanted to use it as an illustrative. Here's, if we could, this would be the ideal system. And then as we just are discussing, Bayesian strategies are complicated, and actually they're extra complicated in the RL setting. So we are going to try to approximate or mimic this without using Bayesian strategies. Okay, let me continue here. So let me tell you also what would be a hypothetical ineffective system. So again, all these questions I've nicely highlighted that the intrinsic reward is internal to the agent. And so we sort of have this underspecified problem. We have to decide what would be reasonable intrinsic reward so the behavior actually does what we want it to do, which is to get good data for the subtask learners. And then that's also going to interact with how good are my subtask learners. If you have really poor subtask learners, it's going to be hard to tell the behavior policy to do anything sensible. So here's an example of an ineffective system where let's imagine we're using SGD with a fixed large step size. So such an algorithm is not going to be able to modulate learning up or down. So if it's, for example, if there's a noisy target and it's just trying to estimate the mean of that noisy target, then it's just going to be constantly distracted by this noise and it's going to oscillate up and down. It's never going to nicely converge down to a solution and stop learning when it no longer needs to see more data. And a correspondingly poor intrinsic reward would be something like the prediction error. This is an intrinsic reward that has been used for problems like this before, although well known to have problems. I'm not the first to propose that this has problems, but still it's a pretty natural intrinsic reward that ends up having quite a few problems. So the intrinsic reward says, if the last action I just took generated some data, I want to make sure, there should have intrinsic reward should be negative of the prediction error because you want the prediction error to be smaller and you're maximizing intrinsic reward. So sorry about that. That should be negative. If you could make the error get smaller after taking an action, that's a good thing. It means you helped your function, whatever your subtask learner's function is, get closer to the target that is trying to predict. So here, for example, the target could be an approximate return with a bootstrap in it, and this would be the action values. Okay, now the issue with this intrinsic reward is that it doesn't actually, it includes these other things that we don't want it to have. Of course, it's going to include something with estimation error. As we get more and more data, we're going to get better and better, or be able to get closer and closer to estimating the best F in our function class. So good, prediction error is going to include the thing we care about, which is estimation error. But it's also going to include information about stochasticity in the targets. So we're always going to have some error just because our targets are stochastic. We're going to estimate the mean. There's going to always be some inherent error we can't overcome. And also there's going to be some bias in our function class that's going to contribute to this as well. And these are two things that behavior policy cannot overcome by just going and gathering data. It can only reduce estimation error. So this is going to be a confusing intrinsic reward because it's going to encourage the behavior policy to forever visit states that are very stochastic or ones that have high bias, which is not at all what we want. Okay, so the point of all this anyway is to point out that this can be a pretty challenging thing to do. And we want to be careful about how we specify these intrinsic rewards so that we actually get efficient learning. And Bayesian subtask learners make it easy to specify a sensible intrinsic reward, but in general, we won't always be able to use them. So we're going to want to answer the question, what about other subtask learners? So I'm going a little bit slow, so I'm going to try to go through this part a little bit more quickly. But I do think it's a good representative example that maybe helps clarify what some of these weights and stuff can look like. So we're going to consider a very small experiment in a bandit setting. Actually, this is part of a larger journal paper in JARE that we have about understanding these intrinsic rewards. We started off in the RL setting and things were so complicated with all the interactions that we stepped back to the bandit setting and really did a thorough study of different intrinsic rewards. And it's definitely been very helpful for us understanding these different properties. Okay, so this experiment just says, let's look at a bandit setting. There's no context or state. That means the behavior policy on each step just gets to pick amongst 4 actions in this case. And there's 1 action per subtask. So there's going to be 4 subtask learners. Each is just trying to estimate the mean of a different target. So these are the 4 targets that are trying to be estimated. And on each time step, these are the targets that a learner could see. So the constant target is very easy to estimate. At the beginning, it starts off away from this constant target, but it should eventually get to it pretty quickly. There's going to be noisy targets where, again, the mean is fixed, but they have a high amount of variance in the target that's sampled. And then there's going to be a non-stationary drifting target that doesn't have too high variance in a short window of time, but it's going to have high variance across time. The update for these is just a very simple LMS update where it's moving its weights closer to whatever the prediction was. And yeah, that's all we have for that. Okay, and so we designed this problem specifically to test what happens when there's some stochasticity in our targets, which can cause issues for things like prediction, the prediction error. And also we like to include this non-stationary target, not because for that question that was asked, because the world is actually non-stationary, but at least it helps mimic a little bit more realistic scenarios where the world can look non-stationary due to partial observability. And it's hard to do anything more complex in a bandit problem. So what we should expect from this problem setting is that a good behavior should look something like the following, where the constant can be learned fast, so that's the blue one, and we should expect that the probability of selecting that action goes down relatively quickly because it's generated enough data for that subtask learner that it should be done. The noisy arms, the noisy targets are harder to learn because there's so much stochasticity in these targets. We're going to need more samples. So the probability is going to be higher for longer, but eventually it should be able to settle on the mean, getting a sample average is not too difficult. So it should be able to eventually settle on that and overcome the noise. And then the drifting target is non-stationary. So it needs to forever select that one so that it can actually track this drifting target. That would be what ideal behavior looks like. Okay, so what we wanted to do here is understand what's the interaction between different subtask learners and different intrinsic rewards. And again, to do this a little more quickly, I'll just point out that we tried the square prediction error, which I've already told you has problems, and weight change, which is a little bit more like that KL. It's just looking at how much did the weights change, so it's better reflecting only how much did the subtask learner think this was helpful for it. Okay, and we also want to contrast good and bad subtask learners, which we're calling introspective and non-introspective. The words good and bad are not particularly descriptive. So the way that we separated out what would be useful subtask learners and not so useful subtask learners are ones that actually try to reason about their own learning. They're going to turn down learning when they've had enough experience and turn it up if the world is non-stationary. So for example, Bayesian learners would be introspective. And what we ended up using was just a simple adaptive step size strategy that slowly decreases the step size, especially in the presence of noise, so that it can actually converge. And a non-introspective one would be something like fixed step size stochastic gradient descent that is just going to constantly chase this noise. Okay, so what we found is that even if you used a good intrinsic reward, what we would think is a good intrinsic reward, but with a bad subtask learner, performance was bad. And so in general, the interactions between all these different settings resulted in bad behavior. And the only time it worked well is when we were careful about picking a good subtask learner with an intrinsic reward that then well reflected amount of learning. So like I said, in the interest of time, I'm just going to have to get you to rely on the smiley faces to believe me about that. And here on the slide, I also have what the corresponding action probabilities were. So you can see that this one actually has that ideal behavior that we talked about, and the other ones all have strange things going on. So the key takeaway from this for us was that designing effective continual subtask learning systems really requires considering interactions between these learning components. So it starts to feel a whole lot more like designing systems, but we really are still trying to design fundamental algorithms here. But when we start integrating different components, naturally there's going to be interactions between these components, and it's going to make reasonably good ideas look like they're bad because we haven't thought enough about the interactions. So our conclusion here is that we need to make sure we have what we're going to call introspective subtask learners, and intrinsic rewards need to be based only on amount of learning and not include these extra confusing factors like stochasticity. I'll leave this open challenge here for anyone who's interested in understanding a bit more theoretically, especially how it is that this connects to what would be this idealized behavior that we're looking for. And we gave some connections, but it's just barely scratching the surface. Okay, I'm going to run out of time pretty quickly here. So let's get back to the RL setting and talk about the other part of the system that I think is very important. So we just talked about identifying intrinsic rewards. That was a really important part of this problem. And right now we're going to settle on the conclusion that we made, which is we're going to use a very simple strategy, that's weight change. And we're going to try to make sure we use sample efficient RL algorithms that use adaptive step sizes. So we're going to not try to fall into the trap where we have weak subtask learners that are going to cause the whole system to behave strangely. And now our next two goals are going to be, now in the full RL setting, we come back to the question of how do we learn subtask learners efficiently from off-policy data, and how do we handle the intrinsic rewards that are non-stationary. And that's going to be much more difficult in the RL setting because RL algorithms really are not designed for non-stationary rewards, they're designed for stationary rewards. And I haven't explained this too much yet, but the rewards are non-stationary inherently in our problem because each time the behavior policy visits a state, the subtask learners all learn something. And so that the next time you come to that state, they might actually all be done learning already. And so the rewards might have been high the last time you were there, but they might be zero the next time you come there. So naturally, we actually expect the rewards to generally be decaying as time passes, except for there'll be some non-stationary, so they might jump in different ways. So these are two really fun key technical challenges that I'll tell you about now briefly. So I'm not going to have a chance to talk about all the off-policy algorithms. But my lab, this might be the #1 topic that we work on in my lab. We have focused a whole lot on designing effective off-policy algorithms. And we actually have a recent journal submission that summarizes a lot of this work, some of our work, but also the larger literature on this very vast topic. And so one thing, the main takeaway from this, I'm not going to talk more about the off-policy algorithms. I do encourage you to read this paper, which I really love, is that we, and by me meaning the whole community, has made a lot of progress actually on making stable off-policy algorithms. Our algorithms are much better today than they were than just 10 years ago, but there's still some cool challenges here about how can we actually make them better, especially in terms of understanding convergence rates and improving sample efficiency. So let's focus on the second key technical challenge, which is the one of non-stationary rewards. Okay, so this is also from a recent paper at NeurIPS just this last year, where our primary focus was for this problem, which at the time we were calling continual auxiliary task learning. We now like the word subtask. Our goal was to answer the question, how are we going to handle these non-stationary rewards? And the key idea that I will actually have just enough time to tell you about is that we use successor features, where we use the successor features to learn stationary feature information and only track changing rewards. So I think this is a pretty neat idea. It's probably the most technical part of the talk, so I think it's worth spending a little time explaining it, especially since successor features are just kind of cool. It's nice to know something about successor features. Okay, so let me tell you what successor features are, and then it'll be almost immediately obvious how it is that we can use them for non-stationary rewards. Okay, so we're going to assume we have some features for our state action pair. We're going to call these features X of SA. And the successor features correspond to the cumulative discounted sum of these features when following a policy pi in expectation. Okay, so what this is saying here is that the successor features are the features in state ST, AT plus gamma times the features in the next state times gamma squared times the features in the next state. And you can see how now this is actually looking a whole lot like a return, just like we had for value functions. We apparently only have one trick in RL, which is this type of recursive form. So we have something that looks just like a value function for these successor features. And now the main difference is just that this is a vector value function. So the size of this vector, let's say, is d-dimensional, 1,000 features or something. Then this psi is going to be inputting states and actions, and it's going to be outputting a vector of size 1,000, as opposed to usual value functions, that's just outputting a scalar. Nonetheless, despite this vector valued form, you can still use all the same value function learning approaches we know and love, including all of our off-policy algorithms. So that's what successor features are. And now you might ask, why is that at all useful? Sure, I could estimate the cumulative sum of features into the future. There might be a question. No, just an accidental sound. So the neat thing about successor features is that if the rewards are linear in the features, so if we have some true W star that produces the rewards in these features, then we can actually immediately obtain the true action values for a policy pi using the successor features. So by just taking the dot product between W star and these successor features. And it's actually very easy to see why. The reason is if we just take this dot product, we can bring this W star into what the psi is defined as. And so now, we're going to dot product each of the feature vectors with W star. This I just told you is corresponding to the reward. So this is the reward in ST-AT. This now here is the reward in ST plus 1, AT plus 1. And now you can see this is turned into a return, and that's just going to equal our Q pi. So it makes sense that learning the discounted cumulative sum of the features into the feature, if then you dot product that with W star, is going to give you the cumulative discounted sum of the rewards. Okay, so again, coming back to why that's useful, since we have this property, now what this tells us is that we no longer have to try to directly estimate Q. We can solve a much simpler regression problem. We can just go try to estimate our immediate rewards using W and using whatever regression strategy you like. And now we're going to get back a Q hat that's going to approximate our Q pi. Okay, so what you should be thinking to yourself is, wait a moment, this seems worse, because we've actually exchanged the easier problem of estimating Q pi with now estimating these successor features, which is this vector valued function. That just seems like a strictly harder problem. So yes, that is correct. It is worse. And so the answer isn't why are they useful. We always have to ask, when would this be useful? And the effort of learning this extra psi is only going to be useful when we get to reuse that psi. And in particular for us, it's going to be useful to reuse that psi because the rewards are going to be non-stationary. So we're going to take advantage of the fact that we can learn the stationary component, which is this successor features, the sum of the features into the future. And then we're just going to be able to track these changing rewards as a simpler regression problem. And the idea here is that tracking changing rewards is fundamentally simpler than tracking the resulting changing value function, which if we are, product out, imagining the rewards have changed, we have to accumulate all the changes in every state along the way, which is going to be harder. And in fact, we formalize this result or this intuition in this paper where we look at the convergence rate and see that it's better than convergence rates for value functions. Okay, so I'm really going to run out of time now. I'm just going to wrap this up so there's enough time for a few more questions. But I'll just show you one experiment where we test out this idea, and we can use this idea of successor features with non-stationary signals for both our subtask learners and our behavior learner because they all use value functions. In fact, I feel like I'm too much out of time that what I'm going to do is just point you to the paper. We actually start the simplest case, which we take what we did in that bandit setting. We now bring it to the MDP, but we still think about similar types of signals that could distract or confuse the agent. And then we ask the question, how much does it help for us to properly tackle these non-stationary rewards? And when we use our successor feature idea for both the subtask learners and the behavior, we see much, much better performance than just using more standard RL algorithms. In fact, we started with this standard setting and we thought, oh, this is a pretty easy problem. Probably these algorithms are good enough. And then we were actually sort of shocked by this result. And we're harshly reminded about our previous conclusion that interactions between components in these systems can have very unexpected behavior. And we really need to be careful about designing each component if we want to have good behavior. Okay, so I'm going to have to skip some of these other results that are in the slides, talking about all the different things we tried. I'll also skip this biggest limitation of our approach. I encourage you to look at it and think about solving this limitation. And then I'm just going to summarize now what I've tried to tell you today. So my goals of this talk were to tell you that general purpose agents, including ones we'll want for our applications, require the system to be built with subtask learning in mind. This continual subtask learning problem formalizes this problem of efficiently learning many subtasks in parallel off policy. And the key points to consider when designing these types of agents is that it's critical to have sample efficient subtask learners that can modulate learning. So I'm going to call that introspective or Bayesian-like. And the rewards are always going to be non-stationary in this problem, in the CSL problem. So the behavior algorithm should be designed to handle this non-stationarity, and that's going to have a big impact on performance. And the key algorithmic insights that we have here is that off-policy algorithms are now mature enough to help us move forward in this problem setting, but improving them further could really have big impacts because of these complex interactions, like I said. And successor features do help us handle non-stationarity. And finally, one that I didn't emphasize too much, but weight change is not an intrinsic reward that has been used before us, but it is a surprisingly effective one. So I'll leave it there, leave it with a list of things that I think are still exciting to do. And thank you very much for listening.
Okay, super. Thank you very much. Okay, so I guess, yeah, it is 2 o'clock. If anybody needs to go, obviously feel free to go, but let's still go ahead with some questions. So anybody who's interested and would like to ask a question, I guess, yeah, please use the raise hand button and we'll go through the questions. So I see here Sayed has his hand raised, so please go ahead, Sayed.
I think you might be muted.
Yep. Thank you so much for the great talk. So I have one question. I understood the part about these subtask learners, and the example you had about that stochastic target and the fact that it was kind of encouraged to take actions for that particular bandit to learn it. But in a greater scale, does it matter how much taking that particular action or learning that particular reward, or let's put it this way, does it matter how accurate I can predict that reward impacts my greater goal to navigate in the system, right? So,
I think I get the question. I think the question is,
Do you have some sort of weighting over these tasks, that how they interact in me achieving the goal? And
yes.
and then if my policy depends on, like, let's say if I use those predictions in a model-based RL, does it matter, like, when I want that posterior probability, does that complicate the calculation of that posterior, the fact that I used these models in taking actions? So maybe two questions I ask. So sorry.
Sure. Yeah, I think there is a lot of stuff to understand. If the agent has identified a subtask, how much does the accuracy of that subtask actually help it with its ultimate goal, which is to maximize reward? Is an important question, absolutely. And right now, we really just assume that once the agent has identified a subtask, its goal is to go get those subtasks as accurate as possible. And as a natural follow-up step is to start asking questions like, how do we balance these subtasks where some might be more important than others? How do we even define the intrinsic reward, maybe so that good enough can be encoded? Like once you hit some threshold, that's good enough and you start getting much smaller intrinsic rewards. How do we even figure out how much those subtasks are actually helping the main task? Those are all really important questions and ones that we have not at all tackled. So I would argue that even if we are not tackling that setting, understanding how it is that we can even get an agent to go actively gather data to learn many subtasks is sufficiently hard that we should tackle it first, and will still inform us even when we start adding these additional nuances.
Okay. So at this point, all of them are equally important.
That's right. They're all equally important, and we want to get them all accurate.
Okay. So I'll let Mark ask question. I still didn't get an answer on my second question, but let's let Mark go ahead.
That's great. Thanks, Martha. Great talk, and like especially on the latter part. You could have a whole other talk and come again for on the successor stuff and their importance, because it's always good to review that and go like, oh yeah, they are powerful. But on the earlier parts about the subtasks and connecting them, what about like observations, or like trying to like observe? This is the thing we're trying to look at, was things where you're trying to do RL for things like science or chemistry, where you're trying to observe something about the world, basically to reduce your uncertainty about the world. So a little bit closer to an MDP than the POMDP, where your action is an observation. It feels similar to this, but I think that's not really what you're talking about, right? But could these subtasks be learning more about the world?
Yes, they could be. Now let me understand what you're saying. So you're saying you're looking at you're trying to reduce your uncertainty about the world. And uncertainty about what?
What state you're in, right? So say your RL, your agent is trying to mix chemicals, and you've done a bunch of things, and now you don't know exactly what state it's in because there's some uncertainty there. You could put it in the spectrometer and get, observation, but it costs you something, right?
Right. I get what you're saying. Yeah, the active perception setting.
Yeah.
Okay, now how is this related to the active perception setting? It's definitely related in the sense that for both, the primary goal of the agent is to take actions to learn something about the world. In your case, like you said, to reduce uncertainty or infer your state. And in my case, to make predictions more accurate. So I would say that I'm not sure how you would exactly represent the goal of inferring state as the types of subtasks I said, which is options and general value functions. So I don't think they're the same. I do think that they'll be different in a way, but there's absolutely overlap between the two because they are both about learning. That's
your subtask could be defined as something else about the world that you're not optimizing, but you're learning, but it's not really about which state you're in more specifically. It could just be anything about that state. Right,
that's true. Now, I guess it is true that you could say that the state that you're in, that you're trying to infer, is like a prediction task. Like, maybe you have a vector, even like the hidden layer of an RNN or something that's like your state. And then so each component is a thing that you're trying to predict. And slowly, as you get more data, you're narrowing around what you think is the most likely state you have.
Yeah.
I don't think you could represent that as a GVF, but it's definitely a natural subtask.
Yeah, that's interesting. And is prediction, is every subtask is always about prediction? Is there any other things that could be? So it's control prediction.
Yeah, we've just been doing control and prediction. In fact, we've largely focused on prediction, but we do want to start learning more about options.
Yeah, great. Okay, thanks.
Maybe Sayed, do you want to ask again your second question?
Yeah, you ask your second question again.
Yeah, sure. So let me actually tweak it a little bit. So when you get these intrinsic rewards, how is it integrated in your RL agent at the end? So that part I kind of missed, and then somehow it has to be circled back, like the interactions between these tasks and the policy that is being executed. Like if you want to learn it end to end, does this interaction matter, or can you just assume that they're independent?
Yeah, so right now I'm not imagining you're going to learn things end to end. Rather, what I'm imagining is the agent discovers for itself somehow the task 1 to task n is useful. And then internally to itself, it generates this intrinsic reward that we've been talking about. And then let's say for this full RL agent, you would just take RT plus 1 plus this intrinsic reward, and the behavior would try to maximize the sum of those two things. Is the most basic way to do this.
I see. So it's equally important to learn these subtasks and also get the reward that I want to get. Let's say deliver the package. For that, I get a reward, and also for learning these subtasks, I'm getting a reward, and these two are equally important.
Well, so what I would say is that we exactly tried not to tackle this question by saying, let's ignore the environmental reward. And I think it's actually an open research question to say, how should we combine these two things appropriately? One of the ways we've been thinking about it is that our agents probably live in worlds where the environmental reward is sparse. So like, let's say that courier robot, it only gets a reward when it delivers things. In between, the rest of the time when it's not doing that, it has zero environmental reward. And so it's really just being driven by its intrinsic rewards. Like there might be these large chunks of time where it just needs to learn about the reward. So there isn't a balancing in those ones. Actually the one example we usually use is like babies, where babies are not hungry, they eat, no, they're not hungry, and they just spend lots of time learning until they're hungry again. And that environmental reward comes more infrequently. And in between environmental rewards, it's just time for learning. So we're sort of looking at, in some sense, that setting apart. Either naturally you don't have any environmental reward, or eventually, as a very important research question is, how do you balance these two appropriately? And we have no answers for that yet.
I mean, to think about it, like when you have these subtasks, you really don't know how important they are, right? You might think that this is important, but then figure out that it was actually not important. It was really important for me to learn how to charge, but it wasn't that important for me to learn how to, let's say, park or do something like that.
Absolutely. Yep. The agent might, in fact, just do discovery by proposing a bunch of subtasks, and now it needs to learn them first. And after learning them, it might realize, okay, that was not a useful subtask at all. And then it might just discard it altogether. I agree. There's going to be some kind of cycle here where it's both discovering and learning and realizing subtasks are not useful.
Okay, thanks.
That's an interesting idea, as you're saying that, like if you guys thought of it being like you're saying the child learning, that you essentially change the weighting where the intrinsic reward stays high at the beginning and then it becomes more and more the reward, the proper normal.
Right, yeah, the intrinsic reward, I didn't hear exactly the last part you said, but the intrinsic reward starts coming down, I think you were saying.
It gets weaker and the standard classic reward just becomes stronger. So at the end, you're actually maximizing reward, but you start off.
Oh, I didn't say that, but I also agree with that. That's true, that there is, maybe in some sense, babies do focus maybe a bit more on the learning part because everything is so exciting.
How their hands work.
Here. Yeah.
And they realize they like food, then.
Yeah, exactly.
So actually, maybe to add to this discussion, so my experience in the past is that if we're doing Bayesian reinforcement learning and we've got some rewards, then the Bayesian techniques will essentially learn to gather information that's useful in terms of maximizing the rewards in the long run. So they will already do the right things without needing an intrinsic reward. But I guess I could see the usefulness of an intrinsic reward when we don't know a priori what are going to be our rewards down the road, like especially in continual learning, I'm assuming that the rewards might change over time. Or if we also have prior knowledge, so just like in reward shaping, sometimes you know that, okay, this is your goal, these are the rewards you care about, and now you think that a certain task could be useful to speed up the learning, but you don't want the algorithm to have to figure this out on its own. So you want to use that prior knowledge because you think that this is going to be useful. So then in the reward shaping, what we do is we say, okay, let's add some more rewards for certain things that we're going to visit, but here it could be for learning a specific task, right?
Mm-hmm.
And then if we don't want the intrinsic reward to overshadow the real reward, then I guess there's a work on reward shaping that says that as long as we use potentials that are safe, that then this won't have this undesirable effect, right? So I guess, Martha, does that make sense? Is that reasonable what I described?
I think it's reasonable what you described, but I would also disagree to some extent a little bit. And one in that way is that often intrinsic rewards are thought of as these secondary things that maybe either help the agent explore better. And often intrinsic rewards right now are used for exploration, but we're not using them as exploration. For us, they are actually our problem setting. And by building them in some sense, what I'm saying is that the agent should be maximizing these. So like, the way I think about it a little bit is that evolutionarily, we have some environmental rewards, but then also evolution has built in a bunch of intrinsic rewards into our brain. But I can't just ignore those intrinsic rewards. They are now part of my environment. It's an inductive bias that's been built into me by evolution because evolution has has realized that learning is good. So in some sense, I'm building that same thing into my agents. I'm saying learning is good, and they're stuck with that inductive bias. Now, sometimes maybe learning that inductive bias might be harmful. It might actually make it so you're not maximizing the environment reward as best as possible. But yet I'm going to commit to that inductive bias is the claim I'm making.
Okay. Yeah, that sounds good.
But then somehow this should evolve, right? Because, when we were kids, we learned like geography, for example, or history and stuff. And at that point, we were so excited about learning them. But then we ended up like someone might have ended up thinking, oh, that was actually not a good use of my time. And now my goal has changed and I want to learn some other stuff, right? So,
totally.
Right?
Yeah, so in fact, that's sort of what Mark was saying as well, is that we're going to learn some things, our rewards are going to go down after we've learned them, but then we're always going to reach new situations. And so like you're saying, you're going to get older, you're going to expand out, maybe you're in university or something, and then you're going to constantly be generating new subtasks for yourself, and you're going to be interested in those, and you're not going to be interested in the old subtasks that you've already learned, or even just are not relevant anymore. Maybe you prune them out.
Okay. Yeah.
So I have another question still related to rewards, but you were talking earlier about non-stationary rewards and how these arise. And because you're in a Bayesian setting, now it wasn't clear to me, are you treating the state as just the physical state, or are you including in the state as well the posterior distribution for the tasks?
Oh, wow, good question. Actually, in some sense, we're not in a Bayesian setting in the sense that we didn't really use Bayesian algorithms for this. What I wish we could use is Bayesian algorithms for this, but we did not do that. And we didn't use Bayesian algorithms for the behavior either. But you are absolutely right that one way to make this problem stationary rather than non-stationary is to take the state and augment it with essentially the state of the subtask learners. And then now you're learning, given the current state of my subtask learners and the state, this is the reward I should expect to see, and that will be stationary. Now that's a large, hard approximation problem. So we've been looking at it instead as a non-stationary problem.
Okay, and then so you're saying it's a hard problem because now your state dimensionality just blows up.
Mm-hmm.
But okay, I mean, I feel like compared to like task in computer vision or NLP, that's probably not much of a blow up, but anyway.
That's possible. So actually, I do think we took let's just try to track the non-stationarity path. A totally reasonable next path, or like a different path, would be to say, let's overcome this partial observability, either by giving the full weights of all the subtask learners to my behavior learner, or some summary of those, or at least use recurrence in some way so you can try to build up this state that you're missing. I do think that that's a fruitful direction that we have not taken.
Okay, cool.
Given that this non-stationarity is like coded inside this, could it be applied to multi-agent settings where you have multiple agents and the non-stationarity comes because of them also learning?
I guess in some sense, this is a little bit like the reason we have non-stationarity in the multi-agent setting. Yeah, each subtask is like a different agent, and then the behavior is a different agent, and they're changing.
Okay. Yeah. Cool. Sorry, I keep asking questions.
Questions are
I'm going to
good.
shut up.
Okay, I do have one more question. So the tasks here, I guess they are defined by the designers, or is the agent kind of learning those as well? And if yes, what parts are being learned?
The ultimate goal is for this all to be discovered within the agent. Like the agent from its own perspective needs to realize it's useful to go to the charger, and it's useful to make these predictions grounded in its own sensors and whatnot. But
Yeah.
we right now in our experiments have assumed that we have designed the tasks and we are giving them to the agent. So ultimate goal is agent discovers the subtasks. All of our work so far has assumed that we designed the subtasks and give them to the agent.
Okay, yeah, because I guess there's a bit of work on learning them too, but it's tough. It's really tough.
It's tough. The discovery question is very tough, very interesting, very exciting.
Yeah. Okay, great. Are there any other questions from anyone?
Pascal, can I ask a question?
Yes, please do.
Hey, hello, Martha. Thank you again for the great talk. So I have one question on this weight change method. So one aspect of that does not seem intuitive to me. So you mentioned that how the weight change is actually, providing some idea about learning. So it's kind of saying how much more you can learn by the difference that you're trying to compute. But towards the end of learning, probably like once the subtask is learned well, then obviously the weight change will be small. But that does not mean like that's what we want it to be. So, but the reward at that time will be low. So I think there is a small intuition that I'm missing about what will happen when the subtask is learned well.
Right. Once the subtask is learned well, then I think we would expect the intrinsic reward to be low, because generating more data for that subtasks is not helping. Like it's done learning at that point. So we would, if a subtask learner was truly done and had the perfect function, then we would hope that our intrinsic reward was 0.
Okay, then we only rely on the external rewards at that point of time.
So say that again.
So at that point of time, then we only care about the external rewards, right?
Right.
So this is like slowly we move from caring more about the intrinsic reward, and then as we learn better and better, we only care about the external rewards after that.
That's right. Now, but it always depends about exactly what you're setting. You're talking about in our experiment, we had a non-stationary target. So that one was never done learning. You always had to track. So the intrinsic reward stayed non-zero for that one. And in the real setting, once we moved from, we took this large setting and simplified smaller and smaller. Once we go back to the large setting, then I imagine the agent should never be done learning, because it'll always generate new subtasks. There's always more things to learn about the environment. So in that sense, the intrinsic rewards will never go away.
Okay. Yeah, so I have another quick question about the successor features. So there was this, it's not very clear to me how these can be designed in the first place, because I think somewhere I saw this assumption that we want the rewards to be linear in these features, right?
Yes.
So for all your theory to hold about things being, for it to actually approximate the value function and everything, you want the rewards to be, you have it in this slide, I think. So how are you going to actually, like, how is it practical to design these features for large problems? I mean,
totally reasonable question. Yeah, how could we ever have it that the reward is a linear function of these features X? Yeah, so the way successor features have usually been motivated, like how this assumption has been motivated, is that you could learn these features, let's say with a big complicated neural network, and then those features XSA would be that last layer of that neural network. And I guess we would hope that we should be able to learn a neural network that is able to predict this, hopefully not too complicated function that is the reward. That's the main idea. But you're right, it's absolutely an assumption that could be violated. In our own experiments, we actually just picked some features that were reasonably good at approximating the reward. But the other literature and successor features does look at learning them.
Okay. And that was possible in your setting because your setting was small, right?
Yeah.
So if you're looking at larger problems, that would be much harder.
Right. If you were tackling a general problem, or like the agent was really in one of these complex environments, it would definitely have to learn these features itself.
Okay. Okay. And the other question that I had was like, you mentioned something about, the current trends in reinforcement learning, or at least the current state of the art in reinforcement learning to be really good in off-policy learning. And that is actually giving us an opportunity to do well in learning subtasks, right? So would it be possible to do some like learning of subtasks using some asynchronous methods, like probably like A3C, which could still be on policy, but you learn through parallelized training?
Right, good question. I am, in this whole setting, I tried to say that the agent learns from a single stream of experience, mainly for the reason that I'm imagining these settings where, let's say you do have a robot navigating a city, it only has that one city that it gets to navigate through, or an assistant agent that's interacting with a person. It just has that person that they're interacting with. There are some settings where it would be not unreasonable to consider the asynchronous setting, where you have multiple streams of experience. Let's say you have a simulator. Okay, your simulator is not a great example. Maybe you're Google and you have a bunch of Google homes in people's homes, and now you could sort of treat that like one centralized agent with multiple streams of experience. So it's possible that you could take that different route. In my opinion, the single stream of experience problem setting is the more realistic problem setting. Most problems are single stream of experience, and there's not as many problems that are the multi-stream of experience. It's a more restrictive setting.
Okay, yeah, that makes sense. Thank you.
You're welcome.
Okay, very good. Any other questions for Martha? Okay, so if not, then thank you again, Martha. So great talk and great discussion. So thank you for visiting us virtually, and perhaps in some near future, maybe we can actually see you in person.
Yeah, hopefully that'll happen. Yeah, thanks so much for inviting me. This was a fun discussion.
Great. Okay, thank you. Bye-bye.